The next speaker is Dr. Nathalie Mignet. I had no French, so. And she's coming from the Université Paris, also an INSERM and CNRS hotspot, of course. And she's talking to us about combination of tumor thermal ablation, cytokines, and lipidic adjuvant provide a distal immune response. So we're looking forward to your presentation. You're still wired up.
So thank you very much for the introduction. I'm very happy to be here, and thanks, Beat, for this wonderful meeting and treats. And so it's a bit complicated to go after Dr. Mogimi, of course, but I'd like to tell you that we are in the Faculty of Pharmacy in Paris and close to the Luxembourg Garden, and it's a very big, very nice city to visit. So in the lab, we're interested in nanocrystals, in all lipid nanoparticles, and ferromagnetic liposomes, mostly for biomolecule delivery. And today I wanted to discuss with you the interest of combining physical methods and drug delivery systems to provide different types of interests that we'll discuss. So we started with the state of the art with this review in advanced drug delivery, where we tried to see whether there were some interest in combining both. And I'd like to show you the studies we have done with ultrasound and microbubbles or liposomes to have different questions that we address in terms of membrane destabilization, impact on tumor environment, or what we're interested in now in having a distal effect. So the first work we started with was the combination of microbubbles with DNA. It was shown initially by Karen Milo in the US that it was possible to co-inject microbubbles and DNA and get transfection. So this is why we were interested in trying to improve the amount of DNA within the liver by combining positively charged now microbubble with plasmid. And the plasmid we've chosen is one of the plasmid that we have designed. It's free of antibiotic resistance. It's in clinical trial right now for hair loss. So this was in a rare disease context, and we chose also to use these lipids that we're working on. So the way we're doing microbubbles is quite simple. As you mix with gas, and then you trying to get as possibly monodispersed microbubbles as you can. There are the system TRPS and optical imaging can allow you to visualize this size that you have on the left. You can also check them by fluorescently labeled by flow cytometry, and then you have this system that you have to do with physical persons to listen to the microbubbles message to make sure that they will give some response in imaging. Because what we're doing actually, we're trying to design check all the parameters of the ultrasound thanks to imaging. So here we're using ultrasound imaging. So all the parameters of the ultrasound that we will use for therapy are evaluated with these imaging studies by looking at the amount of the microbubbles that you get in the liver when you get the optimal signal, and then do we need to explode or not the microbubbles, how long we should apply the ultrasound, and we are looking at the luciferase imaging as a model of the plasmid to have the expression. So all these studies that I made in one slide that took some years was also allowed us to have a sustained release. It's the upper curve, which was compared in the middle curve with the commercially available marker microbubbles. So we have this sustained release of the DNA expression, which can be of interest in certain rare disease. And we also have shown that it was in the hepatocyte that we had mostly this expression. So it's also allowed us to validate the lipids that we have used here and the plasmid. And we showed that we had this sustained expression here. The second idea I wanted to discuss with you was to see whether we could use this ultrasound method for drug delivery with liposomes. So the design of the approach here is that we filled actually liposome with iron oxide for several reasons. First, to have a better accumulation eventually of the liposome within the tumor using a magnet, and possibly observe them by MRI imaging. And then when we see that we have a strong accumulation within the tumor, then we would apply the ultrasound. This was in the context of the new system, MRI IFU, that was developed by Philips and another system. So this is why we wanted to have this full study, where when we apply the ultrasound, the drug is going out because it's a thermosensitive liposome, and we can follow the effect by MRI. So we chose this vascular disruptive agent to be able to follow the effect on the vasculature. So to form the liposome, the iron oxide liposome, the group of Christine Ménager in Sorbonne Paris has a very good setup already. Very good setup to observe this filled liposome that you see that they are very much filled with iron oxide, and this is because we could get an improved targeting effect with magnet thanks to this highly filled liposomes. And the interest was here to have in the bottom in red, you can see that we can increase the release by triggering with the IFU. Already we have at 37 degrees a release, but we can improve it. So the full, basically the purple one is the full strategy with all together the magnet, the IFU, and CA4P, the drug, and we could see that. With a very low amount of the drug, we could reach a similar effect with as regard to the large amount, which is used usually IP. So this was of interest, and we also showed that it was related to a reduced vascular density, which was what we expected from the drug. So this is the second example I wanted to discuss, which is actually the fact that we can promote drug release with triggered systems, and maybe modify the tumor microenvironment, which of course could have some impact for distal effect later on. And we wondered if we could actually use this strategy to deliver gene. So this is the last example I wanted to show you. We kept the lipid that we had used for microbubbles studies and the plasmid as well. But actually it was very difficult to obtain ferromagnetic lipoplexes because of the different charges that you get, and it was quite difficult to make sure that we didn't have free iron oxide and we could really have something homogeneous. So we managed it and to have it, but for the study, for the proof of concept, we didn't go with iron oxide. We used lipoplexes. In particular, because in between we had shown with Dr. Reschert in Belgium that some of our lipids had different adjuvant capabilities. It studied the tier 2 and tier 4 pathways, and there were a lot of different lipids that we have synthesized, which were studied. And so we went for this one, which is a C14 bilayer lipid, and which had interest as regard to iron in this study that they showed. So the design of the approach here, we use the same plasmid, but this time the sequence is the idea of expressing a cytokine, the IL-12, to inject intratumorally to have this proof of concept, and then to apply the ultrasound. For the ultrasound, we worked a lot on the different parameters as well to see whether we could have tumor ablation, immunomodulation, and all this depends on the different parameters that you would use. For the study I show you here, it's we use tumor ablation, and in this case, we haven't followed the primary tumor, which we want it to be completely burned. We follow the secondary tumor to make sure that we have distal effect, and this is what we're looking at. So for the first mice experiment, we used only one tumor, and then we checked that indeed we had removed fully the tumor with the IFU by itself, and complete treatment. And we could see that there was interferon gamma expressed mainly in the complete treatment using the lipids and the DNA, which probably is related to IL-12 or one of the mechanism of the lipids involved. And the second study that we published in Exploration of Targeted Anti-Tumor Therapy was to have a second tumor, and in this case we're following this second tumor. And it's in the middle, so it's not significant at this stage. We can see that we could have a systemic effect with the complete treatment, which is already something very interesting, and this is related also with survival. So we know that this approach actually can work, and there's a lot of the optimization to be made on the former one. Probably also using mRNA would be a good idea. But basically, we know that using this all systems of tumor ablation or release of antigen from the tumor with the physical means shown here, can induce already antigen release, activation, going to the lymph nodes and activating the immune system. You can potentialize with lipoplexes or different types of lipid nanoparticle probably. But here the one we're following the most is actually to have a local effect with hydrogel. So we've been working with Dr. Malafos, who's a surgeon who is using radiofrequency as a thermal ablation in tumor metastasis in the liver. And actually you can see that after 6 months he has a relapse on the different metastases, either that he doesn't see during the experiment, the surgery, or which he can treat for some reasons. And in this case, we adapted an hydrogel to be able to inject while he was doing the surgery to have cytokine release at the same place in Cité. So it's the same here. We do not follow the primary tumor. Well, it was a bit complicated to take this to mice because it's a probe which is used for human. But basically, we're following the secondary tumor here again. And if you see the upper side, the first study that we do with micrometastasis model, we do not have in blue any remaining growth of the. We have a strong survival and no tumor growth of the secondary tumor. These are CT26 tumors, so they're growing very fast. And you can see on the left up that if we re-challenge, then we do not have any growth as well. We have this little boost at the initial. We see that it could grow and then it doesn't, which probably involves the immune systems. And in the case of macrometastasis model in the bottom, which are bigger metastases that couldn't be treated, and in this case we're using anti-PD-L1, and it helps to have to maintain the tumor. So, well, basically I wanted to have this to show you that there are some interest in mixing and combining this physical means with the drug delivery system in for different questions to destabilize the membrane. This is what we have done with microbubbles. We're using a lot of imaging techniques to be able to set up the therapeutic protocol to trigger in a controlled manner the drug delivery, and of course the interest of triggering antigen release to potentialize immune response is of interest right now that we are following hotly. So I hope I convinced you that combination therapy open a wide range of opportunities here. So I'd like to acknowledge all the people who worked on this because for the physical methods, of course, you need physician to have to make sure that you're not doing anything wrong. And I'd like to thank my group. You can follow us on this, and we have all our open papers in this archive. Thank you.
Thank you very much for presenting us this combination of physical therapy with a nanoparticle. And I think we will see probably more of this kind of treatment, hopefully, because there's a need that we combine things. And these are techniques that have not really made it to a lot of tumor therapy, especially magnetic particles, but I think there's still a potential for that.